So, one of the first things I said when the lecture series started is that all we have, in most cases in astrophysics, is light. Luckily, when it comes to our solar system, we can send out probes, robots, sometimes astronauts to go collect samples and bring them back to Earth for us for analysis. We can't really do that for supernovae and stuff. It's way too far away. We don't have the technology to get there in ample time. So, all we have is their light. That takes several years, or thousands of years, some cases billions of years to get to us. And that's all we have to analyze. So we have to put together all of our technology, from the radio to the X-rays, to the optical, ground-based, space-based telescopes, to grasp that information, to get those photons, this light, and break it down to pieces that can give us some information about what's going on. And when it comes to supernovae, there's two main things that we measure that give us a lot of information. And the first thing is, first of all, how does the light that we get from supernovae changes as a function of time? And we call this function, or this behavior, this plot, a light curve. And this is an example of a supernova light curve. I've told you many times that, supernova will blow up, eventually it will start brightening up, and then as the supernova expands, it will start cooling down, and then the light is going to start dimming and dimming and dimming down the tail until it's not detectable anymore. And that's the reason we call them transients, because they last for a certain amount of time, and then they're gone from our point of view, from our field of view. You can't detect them anymore. So, supernova light curve has some features that if you study in detail together with some basic laws of physics, you will understand a few broad things about the star that exploded and the power source that powered the explosion. It has a peak. It peaks at a certain level. Some supernovae are brighter than others. Usually when we refer to supernova luminosities and brightnesses, we usually quote the peak luminosity, how the maximum brightness they get to, that level up here. Some of them brighten up in different times than others. And some of them decline in different ways than others. We're going to get to that later. So, definition. Light curve is a change in the intensity of light in supernova as a function of time. But then you can look at changes of the intensity of light that you receive from an astrophysical object, like supernova, as a function of wavelength. Basically, you break down the light in individual colors, like you do with the rainbow, and you measure the intensity of light in its individual beams of colors across wavelengths, as we say. And this is a spectrum. So a spectrum is light intensity as a function of wavelength. And when you start doing that for supernovae, you start bringing up lecture 2, the zoo of supernova types. You see a lot of different behavior, a lot of different spectra for different types of supernovae. And this is kind of like a collection of different types of supernova. 1b, which is helium deficient, hydrogen deficient. 1c, which is hydrogen and helium deficient. Type 2, which is generally hydrogen deficient and hydrogen rich. And there's several different features for different types that we're going to discuss in more detail. But that's it. Light curve, function of light intensity as a function of time. Spectra, light intensity as a function of individual wavelength. This is how diverse supernova light curves can be for different types of supernovae. Some of them, will look, especially type 1a as we discussed, the explosions of white dwarfs, they're pretty homogeneous. They will more or less brighten up in about a couple of weeks, 14 days, and then it will start declining in a similar manner. Well, there's other ones that have a more weird behavior. Some of them decline in more rapid ways at late times than other supernova. For example, this black line here corresponding to type 1a seems to have a faster decline rate than others. Some of them will have a double peak kind of behavior. You will think that they reach a peak at some point, but then they go down and then they brighten up again. And then there's others that will maintain a sort of like constant plateau of luminosity, more or less. We call those type 2 plateau supernovae for a long time before eventually dropping down. So just by seeing that behavior, how light changes as a function of time, you already see that there must be different things going on for different supernovae. How do you explain that versus that? And why there's so big differences? What's the physical processes that drive this behavior? So obviously that brings up some questions that are worth bothering. Why are the light curves different between supernova type 2 and supernova type 1a? Why type 1a are so homogeneous? Why type 2s? They can have different peak luminosities and different behaviors. And you can even find similarities between subtypes. Why are similarities between certain subtypes? And in general, you can ask an even broader question: why always type 1a supernova are brighter than type 1b, type 1c core collapse supernova? Except if we're talking about superluminous supernova, which is a topic we're going to come to in lecture number 8. So let's talk about what the features of these light curves can tell us. And here's a sample light curve of a supernova that, increases in light, as usual, reaches a peak, declines, and then eventually follows this tail, this decline tail, which is very important. And I'll tell you why it's important. So the three main things that you see when you look at a plot like this, when you look at a curve like that, it's the peak, the maximum that the curve reaches, the duration it takes for the light curve to go up and down, and the rate at which the light curve declines as a function of time, which I call here dLdt decay. Many of you from the natural sciences, you know that this is a derivative, and basically tells us how things change as a function of another variable. So this is how the luminosity L changes as a function of time during that duration. So what can we tell by looking at this time scale, which we call diffusion time scale? After all, as I said, what brightens up supernova is light that is produced that then diffuses out of the supernova, expanding supernova material, but then streams out freely and comes to our detectors. Well, that means that this time scale is probably related to that exact process. It's related to the process of photons diffusing out of the mass of the star that exploded. Therefore, we can use our knowledge of physics. We know how light diffuses through matter, and we know the speed of light. We know how light interacts with matter. And we can use these base laws to figure out how much mass is involved in the diffusion of light. The diffusion mass, as we call it, which would give us a hint, how big was the star that died, how massive was the star that exploded, by just measuring this time scale and making some physical assumption about the composition of the supernova, which we can take a hint on by looking at spectra. That's what spectra tells us. And then we're also going to look at this value, the value of maximum peak luminosity. Obviously, brighter supernovae means that they have a brighter source that powers the supernova. They have something more than others. This something more, I alluded to that in the previous lecture, could be nickel mass, how much radioactive nickel they produce, and usually that's the case. Or there could be something else. And then you have this here. That's very important because most supernovae are powered by the radioactive decays of nickel and cobalt-56, decaying down to iron. And this radioactive decay process has a very characteristic decline rate. We know when you have X amount of nickel-56 atoms, we know how long it's going to average take them to get to the half-life of this radioactive material. We've measured in our labs over and over again. It's pretty much a constant. So by knowing this decline rate, which is pretty universal and constant, we can compare this to the decline rate that we see from a supernova, because eventually, this is at very late times. Look at that. This is 100, 150, 200 days after the explosion. So at this point, the supernova material has expanded outwards and it's become transparent. And you see really, you can see inside the supernova. You can see through the center of the central engine. So you don't have any diffusion effects. Diffusion effects of light take place in this area. Down here, it's pretty much optically thin. It's transparent material. So what you see here comes directly from the source that heats the supernova. And if that decline rate is consistent with the decline rate you see or you measure for nickel and cobalt, that's a definitive fact that, hey, this is how much nickel we have for this event. And this nickel is responsible for powering, the decay of nickel is responsible for powering this particular supernova. Now, over the last few, I would say 20 or 30 years, we're able to be lucky sometimes discovering supernovae very early. And that's why it's important. I'm going to talk about that in extent in the last lecture. It's important to have high cadence automated telescopes when we're looking for supernova, because the earliest we catch them, the more we can say about them. Now imagine, let me go back to the previous slide for a second. Imagine if as we're making observations in the sky, we discovered the supernova when it was at this stage. You can't really get a lot of information about it if you catch it after the peak. Or even if you catch it a little bit before the peak. You don't really know how long it took to get to the peak. Therefore, you don't have a good measure of this diffusion time, which gives you a good measure of the mass of the ejecta of the supernova. So catching supernova, discovering supernovae at the earliest times possible is critical for us to get accurate information about the nature of the star that dies. And that's where the modern technology came in, robotics, automated telescopes, high cadence projects, which really rapidly scan the sky looking for these events, and then we can catch them at early times. Very important. So when we do this business, and sometimes we get lucky before we even have this capability, we catch supernova so early that we see an initial spike of light, which declines very rapidly within 1 or 2 days. That initial spike declines. And then we start seeing the rest of the light, the brightening to the peak and then the decline. So we see a lot of these features when we catch supernovae, especially, type 2 core collapse supernovae, at these very, very, very early stages. What is this? Well, if you think about how supernovae explode, and you go back to the simulations that we discussed, you are producing the iron core collapses. You're producing a shock wave that transverses the stellar mass and eventually gets to the surface of the star and it blows up the star and moves the star apart. This is when this shock breaks out. We call it supernova shock breakout, the process where the shock produced by the explosion reaches the surface of the star, the outer layer of the star, and then breaks out of space, moving the star material apart, ripping the star apart. And when that happens, that's when you can start seeing light. As long as the shock of the supernova is buried deep inside the stellar material, there's no light that can come out that's produced, because the star is still there, still intact, and there's so much mass, the light does not have enough time to diffuse out of the surface. But eventually, when the shock gets to the surface and the stellar material starts to expand, that's when you start seeing first light for supernova. And that burst here, that very brief 1 to 2, less than, sometimes even hours, it lasts even hours sometimes. This very bright burst, which is actually very bright in the X-rays, we've seen this in the X-rays, it's very energetic in the X-rays. That's when this burst takes place, when the supernova shock breaks out of the stellar surface. And then what happens, it breaks out of the stellar surface, and then immediately the stellar material starts to expand. But as it starts to expand, simple physics, it cools. The heat gets lost, and it's cool. So as it cools, immediately the light starts to go down. Then there is something else that brings it back up. So if you look at a supernova like it, there's 2 distinct, I would say 3 distinct stages. The very early breakout stage, the rebrightening stage, and then the late time decaying stage. Just looking at the behavior of light from supernovae. And that very early stage corresponds to the shock breaking out of the surface, and then something else, as the material expands, reheats this material. And in many cases, that's the radioactive decay of nickel and cobalt that you built in the core of the star that exploded. In other cases, there's other things that we're going to talk about. So, now, why is that spike important? Because by measuring, remember, back of the envelope calculations we always do in terms of understanding physical systems have to do with 2 basic things most of the time, space and time. So we want a characteristic length and a characteristic time scale. We know information travels at the speed of light, which is pretty constant. We know the speed of light is. So by measuring this time scale and finding out that it's 1 or 2 days, we can infer a physical scale. Well, speed equals distance divided by time. Solve for distance, you get speed times time. Speed is the speed of light, time is about 1 day. You get to and if you do that, you find out radii, distances, scales, that are characteristic of the radius of the star that exploded. 10 to the 14 centimeters, or 10 to the 13 centimeters. In general, the briefest this duration is obviously the more compact and the smaller radius the original star had when it exploded. So just by looking at this spike here, a lot of information about the size of the star that blew up in terms of radial size. So that's important to count for this region. And then the secondary rebrightening after this initial ping is also important because that will give us hints about the mass, not just the initial radius of the star, but the mass of the supernova ejecta, of the debris that the stellar material that moves apart, as well as the peak of that will give us an idea of how much nickel, what is the input energy, the level of input energy we have in the center that rebrightens the supernova light wave. And now, how can we power supernova light waves? Well, I obviously already told you about the radioactive case of nickel and cobalt, which is the most common process. And we see it in most regular supernovae. We see it in the decline rates of light years of any supernovae. And we can infer how much mass of nickel was produced in the explosion. So that seems to be the case for a lot of events. But then you have some other weirder events, more rare. Some of them are superluminous supernova, which I'm going to come to. This is basically my research focus in my career. That you can't explain this simply by employing radioactive decay. Why? Well, one very simple reason is that if you look at the light curve and you infer how much mass the star had when it exploded, and you find the number, say 10 solar masses, 10 times the mass of the star, and then you compare this mass to the amount of mass of radioactive nickel required to power this really bright supernova, you find something like 12 solar masses of nickel. Well, that doesn't make any sense. How can you have a 10 solar mass star producing 12 solar masses of nickel? It's impossible. So there has to be another mechanism for these very bright supernovae, which I'm going to come to later, that can power the light wave. And there's two very common and two very popular mechanisms that we discussed in the literature. One of them is the magnetic spin-down model. Well, as I said during the last lecture when I discussed core collapse supernovae, right after the core collapse process of massive stars, you're going to form a degenerate dense core in the center of the stars, either a neutron star or a black hole. Sometimes, if you have enough rotation, you're going to form a rapidly rotating neutron star, which is also very highly magnetized, or a magnetar. And these are the most magnetized objects in the universe. Magnetic fields never get stronger in the universe. Magnetars definitely take the crown on this. But this rapid spin down of the magnetars when they're born, they can convert this magnetorotational energy that they have on magnetic field and the rotation to radiation. And by doing that, they can eject that radiation to the expanding supernova ejecta. So you can imagine this magnetar in the center of the supernova, the ejecta expanding around it, and this magnetar in the center spins down, depositing energy to this expanding ejecta. And that's another mechanism that you can power this rebrightening part of this light wave. And by feeding models of how this process works, you can infer the characteristics of the magnetar. How much energy the magnetar had, what was the initial rotation rate of the magnetar, and things like that. Now, this model has one problem that we're still trying to solve. And the problem is that the radiation produced by this process is a very special type of radiation in astrophysics, the synchrotron radiation. It's accelerated by the magnetic field. It's like, you have particles accelerating the magnetic field lines that produce this radiation. And that radiation is not thermal. Which means that in order to get this thermal radiation, this thermal emission that you see from this supernovae, you have to have a mechanism that converts their energy from non-thermal to thermal. It has to thermalize into the expanding supernova ejecta. And we still haven't figured out the specifics of that. It's a very complicated physical process. We're still trying to solve it. So there's a big question mark on this model, but it can produce features that we expect. And my favorite, personally, is this model. We see a lot of stars with mass around them. Massive stars with, and I've talked about this before, I'm going to talk about this again in the future. You see bipolar lobes, you see disks, you see all kinds of patchy material around big stars, which means that when those stars explode, they're inevitably going to interact with this material. The ejecta is going to ram into this circumstellar material, and that interaction, the circumstellar interaction, will produce large amounts of energy that can power supernova light wave. And this is something we regularly see, and we can actually definitively measured in the spectra of supernova, because we see some special lines that are produced when that happens, spectral lines. So a third mechanism for bright supernova, which can power a lot of superluminous supernovae, is the interaction of the supernova ejecta with previously shed stellar material, stellar material. Now let's talk a little bit about light diffusion through mass, because after all, when you try to understand the light curve, and you try to infer information about the shape of the light curve and the physical characteristics, the properties of the star that exploded, you need to understand how light works in matter and how light interacts with matter. And this is a little bit of basic physics here. So imagine this being the expanding supernova ejecta, this yellow hemisphere, just half of the ejecta. Okay? And you're producing a photon here in the center. You produce a gamma ray photon by the process of radioactive decay, nickel, cobalt decay to iron. So that gamma ray photon has to find its way out before it eventually streams out and you can detect it with your telescopes. Now, how does it get from here to here? Well, it doesn't get there in a straight line. Along the way, this is stellar material, highly ionized. There's atoms, usually they're ionized, there's nuclei, protons, neutrons, electrons, more importantly. And this particle, this photon, will interact millions and billions of times with other particles, especially electrons, before it gets out. And each interaction, its individual interaction, will change the direction of this photon. So it will start here, it will move a little bit, interact, then it will move a little bit, interact with another one. Interact trillions of times in a chaotic way before it eventually gets out. Now, the models we use to understand the process of these chaotic interactions that happen, and to get a probabilistic view of how much light is going to be emitted after that process taking place, are very similar to the processes we call Monte Carlo processes that people are using to model the stock market. So you can imagine this is the Apple stock, and usually the Apple stock would just go straight through, it would go up to the ceiling. But then there are other stocks like Tesla Motors, which people lose some trust in this, and they're going to be a little more volatile. So the same mechanism, it's kind of impressive to me that we can apply this physics and this kind of modeling to modeling finance and high frequency trading and the stock market. So anyways, that process is called random walk, and in general we figure out the length of the random walk, which is the length of the entire process for particles to get out of the expanding supernova ejecta, in general scales as the square root of the number of interactions. That's how long this path is. And the number of interactions, well, it depends on how much material you have in your supernova, how many, what's the density of electrons that you have. The more you have, the more interactions you're likely going to have. So the process of random walk is something that we needed to simulate, I'm going to get to that later, in order to understand how light escapes supernova material and what it looks like when it escapes supernova material. But also, the main thing to take away from this slide is that the time it takes for light to, which is what we're after in the end, to escape the supernova material scales as the mass of the material it escapes from, and also another quantity called the opacity of the mass, which is related, it's related to what the material is made of, which I alluded to in my previous statement. So, opacity basically tells you how opaque and how transparent your material is to light. And that depends on how many free electrons you have, for example, because the more free electrons you have, the more interactions the light will go through. So, and that depends what kind of material you have. If you have a hydrogen, you will have 1 electron per hydrogen atom. If you have a helium, you have 2, so on and so forth. So the composition of the supernova ejecta tells you something about the opacity or the transparency of matter, which is a function which determines how many times this photon is going to interact before it escapes. So opacity, which relates to composition, and mass related to the time scale. And now, I put a straight line here because I want you to all forget this after this lecture. but I'm going to look to this very briefly. I just want to show you how complicated things can be in reality when you try to model supernova light curves. So let's take a step back and try to understand step by step the process of radioactive decay, nickel and cobalt, as it powers supernova explosions. So initially you have the so-called homologous expansion of the ejecta. We call it homologous because if you were to measure the speed of material as a function of radius, it looks like a straight line. So V equals R times R divided by T. It's pretty simple. It's a simple law of expansion. So let's assume that the supernova ejecta expand homologously, and then the power source that, in this case, radioactive nickel and cobalt decay, that powers the rebranding of the light curve, it's located in the center, in the core. And that's important. I'll come to that later. In reality, when you do three-dimensional simulations, you see there is some mixing in. It's not, concentrated in a ball in the center of the ejecta. But let's assume, for simplicity, for now, that all the energy that you input to the supernova ejecta is concentrated in the center of the ejecta, in a narrow ball in the center. And let's assume that radiation pressure is dominant. What that means, well, you have material pressure and radiation pressure in reality. It's all pressure, all adds up to pressure, but the difference is that material pressure is the pressure that you're going to get when you try to squeeze a gas into a box, for example. It's all the interactions you get from the individual atoms that resist of the gas, that resist you trying to squeeze it down. That's the pressure, okay? That's the normal pressure. But then you have the radiation pressure, which is the pressure exerted by light, by photons themselves. It has somewhat different properties. Those supernova explosions are so energetic and they have so much radiation that the radiation pressure dominated at this level. And then when you put down these three assumptions, you can make a simple model about how you expect the light to look like as a function of time, taking into account that it has to diffuse, as I showed you in the previous slide, through that material. To do this, you use one of the very popular laws of physics, the first law of thermodynamics, which is basically energy conservation, coupled with this process of radiative diffusion that I described in the previous lecture. And this basically, I'm not really going to go into that, but what it really says is that the change in the energy that you get for the gas, plus the change of the mass, the work you put to expand the supernova, the PdV work, P is pressure, V is volume, has to equal the amount of energy you put in by the nickel and cobalt decay, this is L in, minus the energy you lose by radiative loss, by the energy you just lose, the radiation you lose as the supernova expands. And when you do this, and you make these assumptions, you end up predicting that, and you solve for L, this is a differential equation. So it's not something, x minus 2 equals 0, x equals 2. So this you have to figure out, you have to find a function if you solve it. This is the evolution of energy as a function of time, d dt, and this is the evolution of volume as a function of time, dv dt. So you have to solve for L, which is also a function of time, and if you do that, this is the solution. And I'm going to leave it at that. That basically tells you that if you plot this in a plot, it will look like this. Okay, let's just leave it at that. It will look like that, and what you really care about is to figure out what parameters you should put into this mess to fit what you see with your telescopes. So your telescope is going to give you data points of how supernova goes up and goes down, and then it's your job to put this model in and select those individual parameters in a way that will fit what you see. And what that will tell you, it will tell you something about, for example, the radius of the star explosion, R0. It will tell you something about the time, Td, which is related to the mass of the supernova it takes for light to diffuse. So Td will give you an idea of the mass of the supernova. V is the velocity of the expansion, and you can measure it in the spectra. So that will give you an idea about the physical properties of supernova. So we do that a lot. As a first step, we use those simple semi-analytic models that I just showed you to fit supernova light curves. This is an example from a paper, from a publication. You see a supernova 2003 JD marked with filled squares, and unfortunately we didn't catch them that early. We caught it a little bit before peak luminosity and then decline, and then we fit several models based on the previous equation. And by fitting those models, we get this variable, Td, diffusion timescale, which, as I said, gives you an ejecta mass. of the supernova ejecta. And this equation simply tells you that the ejecta mass scales as the square of the diffusion time as the velocity of the supernova of the expanding ejecta, and it's also inversely proportional to the opacity. Kappa is the opacity of the material that I talked about before. Now this is better the constant, and c is the speed of light. You know, when you do something, even in the back of the envelope way that involves the diffusion of light, you expect the speed of light to be part of the equation. You know, by definition. So there it is. Yeah. Good question. So as I said before, in core collapse supernova, 99% of the explosion, the efficiency of the explosion goes to neutrinos that directly escape. And it's only the 1% that stays back to push the explosion. Yeah, but then from this 1%, you tap even a lesser amount. You know, you have radiative losses. So, you know, and that changes from supernova to supernova. So initially, when you have a core collapse supernova, for example, you have a 10 to the 53 ergs. Erg is the unit we use for energy in physics. One of the units we use. But in reality, what comes out radiatively is 10 to the 51 ergs. About the hundredth of that. And a small portion of that is lost as well in the radiative processes. So, okay, so we have a simple way, an analytical model that I described before, to capture the main characteristic of supernova just by looking at light curves and fitting light curves with this model, okay? But then there is, again, as I showed you, a zoo of light curves. There is some, they don't simply do that and then that, or like this one right here. Some of them have a plateau. How do you fit that to that model? Well, you're missing something in this model. You can't fit that type 2P or type 2 plateau light curve with that model. It would be a horrible fit. It wouldn't give you any useful information. So the progenitors of type 2P supernova, which are actually one of the most common type of supernova explosions, are thought to be red supergiants, really large radii stars. Red supergiants retain the hydrogen envelopes in the outer layer before they become supernovae, and they have radii of 10 to the 14 centimeters or 10 to the 1 billion kilometers diameter. This is pretty big stars in radius. And all these outer materials made of hydrogen. So now hydrogen has when you have light interacting with matter, you have other things that play an important role, like temperature and pressure. When you subject hydrogen gas in temperatures higher than a certain threshold, for example, in this case, it's pretty well-known threshold, it's 5700 Kelvin degrees. If you subject hydrogen gas more than this threshold, you're going to ionize it. It gets so hot that the electrons are going to start escaping the atom, the hydrogen atom. You're going to ionize it. So you're going to have electrons and atoms. You're going to have a plasma, in other words. When that happens, the properties of the opacity are different. That goes back to the opacity because you have more free electrons. You know? So these stars have so much hydrogen outside that by the time they start expanding, the temperature is held almost constant and the opacity is held constant. Because you need to get to that temperature, you need to drop below that temperature threshold to start recombining electrons back to the atoms. So as long as you're in this stage, this plateau stage, the reason you maintain your luminosity almost constant is because you haven't yet reached that threshold. You still have really hot material, which means that all atoms are ionized, electrons are free from atoms, and that keeps the temperature more or less constant, and the opacity. But eventually, that ends. You know, the supernova expands way too much, it becomes so cool, the temperature drops, so material starts to recombine. So electrons start to go back to atoms, and that's when you have this really sharp drop of the light curve. So in reality, the previous equation that I showed you before becomes even more complicated and long if you incorporate this. And we can do this, and then we can figure out, for example, okay, how much hydrogen we have in this type 2P supernova. How much hydrogen you need to produce this long duration plateau phase. So, yet another variable Feeding supernova is not easy. And this is what we do all the time. To get, the first thing we do is to look at light curves to get some basic information about the star. And let's look at some tangible results that have been published in papers over the years. So in all of these three different examples, I have an example of a type 1a supernova, pretty standard white dwarf explosion. An example of a type 2 supernova 197A, our favorite, type 2 peculiar supernovae, and a hydrogen and helium poor type 1c supernova. And all those light curves look different in terms of peak luminosity. So the y-axis basically is luminosity, and the x-axis is days, duration. And you can see they look different in peak luminosity, in terms of decline rate, in terms of diffusion time, or how long it takes to go up and down. So we fit these models that I talked about before to all these events, and this is what we get. For this type 1a, we estimate that to power this maximum, this peak luminosity, we need about half solar mass of nickel, of radioactive nickel. And we need an ejecta mass of 1.45. Look how that is close to the Chandrasekhar mass, which is the characteristic mass of white dwarfs, 1.45. And this is how much energy we estimate. Now, for this one, we get a much smaller nickel mass. It's a much dimmer event than this. For that, a little more, but still dimmer than that, brighter than this one. And a smaller ejecta mass. So, just by looking at that, we get a lot of information. First of all, we answer the question why type 1As are brighter, consistently brighter than type 2s. That's because they produce more nickel. They just make more radioactive material that powers them to a brighter peak. And the thermonuclear burning of carbon and oxygen of white dwarfs in type 1A supernova typically produces 0.5 to 0.7 solar mass of nickel. While in typical core collapse supernovae, you'll likely get a 0.1. Except, in some cases, this is a bright case, in some cases we get superluminous supernova, which I'm going to come to later. But those are rare events. So, not only you can get information about how much nickel you need to power these explosions, but you also get information about how much ejecta mass. So, for example, this tells you that the star that died here had less mass in the supernova ejecta, 3 solar masses, than the star that died in this case. Which kind of relates to the fact that hydrogen-poor supernovae, 1Cs, must somehow have lost their hydrogen-helium envelopes. So therefore they have less material for light to diffuse through. So that's kind of consistent with that picture. So, you get some useful first information just looking at the light curves. But that's not the end of the story. We have to do 3-dimensional, complicated radiation transport calculation in order to accurately capture the characteristics of supernova explosions and try to match them with the observations. Those simple analytical models that we have been discussing will give you a broad idea, but if you actually want to nail it down, the details, you need to do very accurate computer simulations, which means that you need to explode these things in 3D, preferably, and then model the diffusion of light with Monte Carlo, with other ways, in great detail as it happens, to not just predict the light curve, but more importantly, a few of my colleagues like to say, Spectra is truth. You can get 2 different types of supernova have similar light curves sometimes. So if you just look at the light curve, you don't see a difference. You say, oh, this is the same kind of object. But if you look at the spectra, they're so different. So Spectra is truth. Spectra contain the most of the information we need to harvest from supernovae. So modeling spectra is a very, very, very expensive computationally and a very complicated business. And we do this by creating codes that can do this. Some of these codes are, thousands of lines long. Some of them are millions of lines long. And the data that we get are what we need to do this accurately. For example, in some codes, we need to know the opacities exactly for its different material, for all the series of materials, and for all different levels of ionization. And that, to model the spectral lines. And those are billions of opacities. So to get the database of this data is huge, and you can only get it by big laboratories that have done the measurements, like Los Alamos, for example. We can measure the opacity of material in laboratories, and that's the ones we use when we build those codes to try to understand, to model the spectra of supernovae. So those are called radiation transport. So there's two types in general. There's radiation transport codes, the ones that deal with the transport of radiation through material and predict you something about the spectra and the light curves of events. And there's radiation hydrodynamics codes, which in detail try to understand the interaction of light and the effects of light, of radiation, to matter itself. So you do both in reality to do this problem correctly. And those numerical techniques are so complicated. So you have these broad categories, and these names down here are examples of codes that can do these kind of things. This is FLAS. We're the FLAS Center of Computational Science here at the University of Chicago, so we like to advertise our code a lot. And FLAS can now do some sort of radiation hydrodynamics. Actually, me and my colleague who sits in the audience, Klaus, we are the ones implementing these new capabilities of FLAS to calculate the interaction of matter with radiation, including the effects of dynamics. Then you have simple radiation transport codes, which look at the broad effects of the diffusion of light through matter. And this is some examples. More detailed Monte Carlo simulations, which go back to that picture of multiple scatterings of light before it escapes. There's some codes that can do that. And there's more complicated methods that we're going to talk about, radiation transport methods that are used in different codes. But one thing, if you go online and try to Google all these names of these codes, you will immediately discover that out of all these, there's probably like 2 or 3 that are publicly available. So you can download FLAS and run it. If you knew how to do it, it's going to be a big learning curve before you know how to do it. But you can download and do some, some simple radiation hydrodynamics. You can download SNEC and, model some simple light curves. And you can download the TARDIS and model some simple spectra. But most of the capabilities of this code that are important are not public for good reasons sometimes. So with the same physics that you can do this, you can simulate nuclear explosions and nuclear bombs. So the US government don't want people to download codes that can simulate nuclear bombs. Although it doesn't really make a big difference anymore, because other countries like in Europe, for example, they have more relaxed criteria on that, and they have already released some of that information. So in principle, someone who wants to do it, they can do it. And I think they're going to be lifting those regulations in the US very soon as well. So anyways, the key here is that unfortunately only a minority of these codes is available for public download. FLAS is one of those, so we're proud of that. That's the whole spirit of our team. So when you do this and when you run these codes, what are you really going to do? So how are you going to model supernova and get spectra and light? This is our goal in supernova, in general astrophysics. Produce a model that will be directly compared to what you see through your telescope, the observations. To do that, it's a lot of work. You need to have a star first, a model of a star. How do you get a model of a star? You use MESA, which is the code I tell you, for example, that has to evolve the star from birth to before it gets supernova. But MESA cannot do all the business, because it cannot do hydrodynamics radiation. It can do the evolution. So then you need to map that model into something that can do the hydrodynamics and the explosion of the evolution. That can be FLAS, for example. So you put that into FLAS. Then FLAS will get to the point where the supernova shock will break out of the star, the supernova ejecta is going to start to expand, and then you need to find a way to calculate spectra. Well, FLAS cannot do spectra, but you can take the information from FLAS of what the material looks like when it expands, and map it into a code like Sedona, and try to do the spectra, which will do Monte Carlo. And you do all this complicated process just to estimate light curves and spectra. And when you do this, this is what you see. This is examples of what the codes give you. This is not observations. This is predictions by those simulations with code after a lot of computer hours run. So for example, this one shows you a prediction of how the light, so the solid line shows you a prediction of the light curve for a certain event. As you can see, none of them seems to fit perfectly, but you get more or less a behavior that you can look at, and information about how massive was the star, for example, and so on and so forth. We've used, this is from a paper we wrote, I read this here, and we use Phoenix, one of my collaborators, who is in my office mate here, Dan Manos is one of the developers of this radiation transport code, so we worked together. And I gave him some models of some hydrogen-poor superluminous supernovae, type 1Cs, and he ran them through his code, and he got spectra, model spectra, and the colors you see here corresponds to different materials producing these features. So, you know, if you look at the blue lines, that means that there's a lot of magnesium responsible for producing that certain feature. Yellow means there's a lot of helium responsible for producing this feature, and so on and so forth. An important thing to do when you're in this numerical business of writing code and making predictions is, you know, it's you and there's another, like, probably 6, 7 people in the world that try to do the same thing. Like, this is a very small number of people that try to do that. Now, then you have sometimes you have 6 or 7 different answers for the same thing. So it's very important to benchmark. It's very important to do code-to-code comparison efforts. So take the same thing, run it through my code, and then also run it through, you know, Sedona, and compare to see whether you get something that looks the same, or because we all have to get the same answer using the same physics. And we've done this at some level, and we are getting agreement with some of the main codes that are used out there, like Sedona. So our code, the Phoenix, does not use the same method to calculate spectra as Sedona does, but if you compare them for the same input, you get a very consistent answer, and that's nice. It's nice to see agreement between different codes. So, to summarize, all we have is light, and we are in the business of deciphering information from light and trying to feed it to what we see through our telescopes. And we do this by looking at supernova light years and supernova spectra. Supernova light years, based on their peak luminosity, that will give us an idea about how much energy was injected in supernova. And based on the duration, they will give us an idea about how much mass was involved in the supernova and the radius of the star that exploded. We can do some simple back-of-the-envelope-ish analytical models of nickel and cobalt decay, for example, and try to figure out how much nickel we need to power some supernova explosion. And we can get broad predictions about several observed supernovae. But in reality, what really needs to be done, and we're doing it, is to get sophisticated numerical codes to do the business of accurately modeling the diffusion of light through matter and predict spectra, because spectra is truth. Light years will give you information, but spectra will nail it. Will tell you exactly their composition, what kind of star you have that exploded, and so on and so forth. Spectra is really hard to model, and there's an armament of codes out there that try to do spectral modeling. And we're doing this for different codes, and we get agreement in most cases, which is encouraging. And the ultimate goal, of course, of this numerical astrophysics is, at this point, we're computer scientists. You know, we're astrophysicists, but we're also computer scientists, because we have to translate those laws of physics, we have to discretize them, and translate them into a thing that a computer can understand, which can solve it much faster and more correctly than we can. And then we have to translate it into a language, and put it in a way that's efficient to solve. It's a complicated business to do computational astrophysics, but ultimately, you need to do that in order to make serious predictions and serious interpretations about things you see through your telescope. Nature is complicated. Thank you very much. Questions? I'm sorry? Yeah. 3D is the ultimate goal. I mean, you know, nature is three-dimensional. Of course, it's very expensive computationally. It's really hard to do. It's very challenging. Some people just do it in pieces. They just break the problem into smaller pieces and they do a 3D model here. And whenever they can avoid 3D, they will do it because they don't have enough computational time. But ultimately, that's what you want to do. You want to do the entire thing in 3D. Oh, they are. The codes are able to do that. We don't have the computers to do that. Even these big supercomputers and Argonne and all these facilities, we can do a lot of things with them, but we can't really do the entire process, you know, from birth to death in 3D. It's very expensive. Yeah? The speed, not in these explosions, not in these explosions. So in gamma ray bursts you can get, the relativistic speeds and so on and so forth, and that is more relevant to gamma ray bursts, which I talked about last time. But in this kind of simple supernova explosion, you don't get to the speeds. You probably get about a tenth of the speed of light, or so. Yeah. Other question? Yeah, you and then you. Yeah. We are already doing that. Yeah. X-Files. Repeat the question because I got X-Files. You can, okay. There's a whole field we call laboratory astrophysics, where we're trying to reproduce the behavior that we see in astrophysical systems in small scales. So, for example, routinely people do white dwarf atmospheres by blasting lasers together in laboratories. So, you can do things like that for sure. I mean, people even look at the possibility of discovering, tiny black holes out of this experiment. No danger, don't be afraid. But they try to simulate conditions as soon as the Big Bang took place, and a few seconds after the Big Bang. So obviously this is the ultimate goal. It's called laboratory astrophysics. But we do get some information from that. Yeah, it's useful. Yeah, but you can't get anything from. I mean, you will get a glimpse of very, very fast behavior that you can measure, but you're not going to get a 2-week, and you don't want to do it. 2-week life of supernova. Yeah, there's a lot of data. There's a lot of data that come out of this experiment. Yeah. Yeah, it's not like they're throwing away the data. It's like they store it and they're storing a lot of that. And they're waiting for people to be hired, like graduate students, cheap labor, to do the dirty work. Yeah. Yeah. No, you gotta work together. Laboratory astrophysics, computational astrophysics, and observational astrophysics gotta work together in many of these problems to get the best we can. He was first, and then you go. Yes? Yeah, so you are right about the part that dark matter plays a role in trying to understand galactic rotation. You need this extra material to explain the rotation you see. But the effects of dark matter become important at this large scale. So if you're talking about the scale of stars and supernova, they're not important. Yeah. Yes? In the center.
But they're also being formed as this is going on. Has anyone, in other words, the dynamics of the system are really very complex?
That's what we do with these codes. That's the ultimate, that's exactly what we do with these computer codes that I talked to you about. Yeah. Exactly. It's the physics of the dynamics is boiled in the computer code we're solving for. The equations of dynamics, equation of nuclear synthesis, everything. Nuclear physics, everything, and that gets solved, in every single time step. Yeah, of course. I mean, actually, if you remember the equation I showed you, the very long equation that we use to get some idea about light years, this is based on the first law of thermodynamics. Okay? Yeah. Yeah. Yes, sir? Yeah. Less than this. Two answers to that question. So he's basically asking why it's important, is it a big deal to actually capture this first soap breakout burst that lasts 1 or 2 days or less than that before the main rebranching? And the answer is yes, because A, this little short breath, this little short, almost said breast, I'm sorry, burst will give you information about the size of the star. You want to know the size of the system that exploded, right? And the other one is that the brightness of that burst is also going to give you some idea about the energy of the supernova shock that expanded. I mean, you can see it in the X-ray. So it's X-ray information. Oh, and there's B. And there's B is that, again, you want to capture these events as soon as possible, because if you were to measure the light or the mass that the light diffuses through, you need to have the rise and the decline. The earlier you catch the rise, the more you can constrain it, the more accurate you can see it. In the main duration like it, in the early, you mean the first 1 or 2 days? Well, they are now, because we have technology that can do it very accurately. And you have high cadence telescopes that really rapidly scan the sky and look for these things. So yeah. It's important, and we do it in decent accuracy when we can. Yeah. Next lecture. It's all going to be about Supernova. Yeah. Both. Yeah. I mean, for 97A, it was 97A spectacular because it wasn't just the spike and then the rebranding. We even saw the 7 neutrinos, before everything happened, because neutrinos escaped before everything else. So we captured neutrinos from this event. That's why it's so special. Yeah. Any other questions? All right. Thank you very much. Have a good weekend.